Okay, why don't we go ahead and get started. So welcome back, everyone. So as I said, we have 3 talks. The first talk is by Giuseppe Vietri, and it's on private reinforcement learning with PAC and regret guarantees. So Giuseppe, if you want to share your screen and take it away, please do.
Okay. Thank you, Michael. Okay. So my name is Giuseppe Vietri. I'm a third-year PhD student from the University of Minnesota. Today I'll talk about my work on private reinforcement learning. This is joint work with Borja Balle from DeepMind, Akshay Krishnamurthy from Microsoft Research, and Stephen Wu, who is now at Carnegie Mellon University. This work also appeared in ICML 2020 this year. In this work, we consider online learning with a fixed horizon MDP over a sequence of episodes, where the MDP is defined by a finite set of states, a finite action set, a reward function, transition function. The age is the time horizon of each episode, and we assume here that T is the total number of episodes. For privacy, we assume that the agent interacts with a single user on every episode, and the sequence of states and rewards generated during the episode, it's the sensitive data belonging to that user. For a motivating example, we consider healthcare. For example, reinforcement learning has been used for epilepsy treatment, and in a work by Gus and author from 2008, they showed that they were able to use reinforcement learning to reduce seizures in rats by 25%. And this is a picture of the model. So an agent receives data from a sensor in the rat's brain, and there is and the agent generates a policy that sends electrical signals to the brain. So for human applications, we will consider this as sensitive information, and so it will be useful to have a private algorithm. Our contributions are as follows. First, we provide a formulation of joint differential privacy in reinforcement learning. Then we provide an almost optimal epsilon joint differentially private algorithm with PAC sample complexity and regret guarantees. And we provide lower bounds for a general class of reinforcement learning algorithms that satisfy joint differential privacy. Our results are summarized here as follows. Suppose that the target accuracy is alpha. Then the PAC sample complexity is upper bounded by this term. The first term matches the sample complexity of the non-private algorithm. And the second term is the sample complexity due to privacy. And from this term, we can see that the sample complexity due to privacy is very small when the alpha is very small. So we can say that the cost of privacy is almost negligible when alpha is small. And our lower bounds show that the sample complexity due to privacy or bounds are tied in, at least in the epsilon parameter. For our regret results, we see that the regret at time t is upper bounded by this term here. And again, the first term matches the regret of the non-private algorithm, and the second term is the regret due to privacy. And the regret due to privacy has a lower dependence on t. So when t is very large, the cost of privacy is also negligible here. And again, we show upper bounds for regret, which match on the epsilon parameter. Again, we assume that on each episode, the agent is interacting with a single user, and the user can be represented as a tree of depth H, which encodes all possible state and reward paths. And so we say that the input to a reinforcement learning algorithm is a sequence of T users, and the output is a sequence of T actions where each action is sent to the corresponding user, and a final policy. So at the end of T episodes, we are outputting a final policy by T. Our definition is based on joint differential privacy, and is inspired by a work by Sharif et al. From 2018, where they provided a joint differential privacy definition for contextual bandits. We say that two user sequences, U and U prime, are T neighboring if they are different only in the user in position T. So our definition says that a mechanism M satisfies epsilon joint differential privacy if for all t and all t neighboring user sequences u and u prime, then the output distribution of the mechanism on all episodes before episode t and after episode t is closed under u and u prime. So in other words, if we change the user in position t, then the behavior of the mechanism doesn't change too much for future episodes after episode t. Our algorithm is called private upper confidence bound, PUCB. And this is a joint differentially private version of the UVEB algorithm by Dan et al. This algorithm balances exploration and exploitation using optimism, as in the non-private case. That is, on each episode, we construct a Q function with differential privacy, which we denote by tilde for private. And then after we construct this Q function, the agent follows the greedy policy. That is, on each state S, if it chooses the action that maximizes the Q function value on that state. To construct this Q function, we use event counters that provide sufficient statistics to estimate the Q function value. Here, N hat keeps track of the number of times the user visits state action SA. M hat keeps track of the number of times the user visits transitions from state S to S prime after taking action A. And R hat is a total reward received on the state action SA. To implement privacy, we use private counters, which we denote by tilde. And we use the binary mechanism from Dork et al. And Chan et al. To implement these private counters. And so from that, in those papers, we see that the error of the private counters is upper bounded by this variable E epsilon, which is equal to H over epsilon times log T. So this is an overview of how the algorithm works. First, we initialize the private counters using the binary mechanism. Then on each round T, for each episode T, we first compute a Q function, Q tilde plus, which is equal to, so the value of the Q function of state action SA is equal to the estimated immediate reward plus the estimated expected reward plus a bonus term to make sure that this is a optimistic approximator. The bonus term is composed of two parts. Phi tilde is the sampling error, and this term is from Dan et al. Previous work. And this is a function that grows with the square root of 1 over n. Then, and the psi tilde is the error due to privacy. And this is a function that grows with 1 over n. So the error due to privacy is shrinking faster than the sampling error. After we compute the Q function, we just play the episode following the greedy policy. So on each round H, we choose the action that maximizes the Q function on the current state. Then we observe the reward and the next state. We increase the private counters accordingly. And then at the end of the episodes, we output the sequence of actions and the final policy. To show that the algorithm satisfies epsilon joint differential privacy, we use the Billboard lemma from Su et al., which says that an algorithm is jointly differentially private if the output sent to each user is, number one, a function of the user's data. So in the equation on the right, we can see that the output sent to user T is AT. And this depends on the current state of that user, ST, which is part of his private data. And number two, a signal computed using differential privacy. And this is the Q function, which we already saw it was computed using the private counters. So the Billboard lemma applies here. The sample complexity analysis follows 3 steps. Number one is to construct the optimistic Q function using the private counters and to show that this is in fact optimistic so that the Q tilde plus is greater than Q star, where Q star is the Q function given by following the optimal policy. Then we do an optimality gap decomposition, where on each episode T, we upper bound the optimality gap in that episode by the sum of the confidence terms, by the bonus terms, times the probability of visiting that state. And lastly, we bound the number of episodes where the optimality gap is greater than alpha. And this gives us our sample complexity. Steps 2 and 3 are similar to prior work. And so our main technical contribution is to constructing this Q tilde Q function. To conclude, we provided a meaningful formulation of joint differential privacy for reinforcement learning. We provide an almost optimal algorithm that satisfies joint differential privacy, lower bounds. For future work, we are considering extending this analysis to linear NDPs, where users come equipped with a content, and the dynamics and the rewards depend linearly on these contents. We think this could be a more realistic scenario to analyze for privacy. We also want to run interesting experiments to validate our results. And finally, we believe there are many opportunities to extend this work for other scenarios in reinforcement learning, like batch learning or safe reinforcement learning, and so on. For the full version of this work, you can visit my website. I will also be putting these slides in my website.
Great. Thank you, Giuseppe, for the talk. So we do have time for questions. You can feel free to post a question in the chat session, or you can also unmute yourself and just ask the question directly.
I have a question. So you have this new definition defining JDP for reinforcement learning. Can you talk us through what are the important technical differences between this and just the standard JDP definition?
The standard JDP definition. So this our definition. This is a definition of joint differential privacy under continual observation. So the data comes in sequentially. The idea is that we want to make sure that if a user changes his data on episode T, then the behavior of the mechanism is not affected on future episodes.
So should I think of this as being like JDP under continual observation?
Yes.
Okay.
Mm-hmm.
I have a question as well. So if I understood the kind of parameters correctly, so that there's H is a key parameter, which is like the length of the episode. And I'm wondering,
H, yes.
And it seems like the error grows with H, which seems on the one hand sort of fundamental because you're getting more information with each state. But I guess I'm wondering in a deployment context where that you're using reinforcement to learn a pattern that maybe is like stable over time. Is there a way that you can sort of like eventually stop learning and converge, and even if users have like very long episodes, that there isn't additional privacy cost after a certain point?
Yeah, so you're referring to the error in the sample complexity.
Yeah.
Yeah, so your question, if the episode, the H is large, then you may not be. Mm-hmm.
Yeah, I guess if I understood, like T is like the number of users, and then H is like the length of a user's sort of sequence.
Right. Yeah.
And so like if you were to deploy this, like you might have a system that's like running forever, right? So H
Right.
would grow unbounded. So is there anything, I guess, you can do in that context? Like maybe you stop learning at some point if you can converge to some like stable policy or something?
Yeah, so if the H is unbounded, I'm not sure if we can do anything because so the H gives you the total number of observations for each user, right? So so you have to calibrate your noise to right. So if you can have unlimited observations, I'm not sure if this will apply or converge to anything. Yeah.
Okay. Okay. I don't see any other questions. So let's go ahead and thank Giuseppe for the talk. Thank you, Giuseppe.